Okay, transport layer. I'm going to skip the chapter one. You may be able to read them. Transport layer is very, very important where you can see the two protocols, two very, very, let's see. Okay. Uh, Two protocols, particularly the protocol that I want you to understand is UDP and TCP. And what do we mean by connectionless and connection oriented? From your midterm, as far as you said, connectionless and connection oriented, to differentiate UDP and TCP, that'll be okay. Some of you, Anthony, Did you? Did you answer that way? Oh, great. You complained. Differently? But it's like a connection and connectionless? That is, but technically, uh, that's right. Yeah, for emails and so technical difference is that UDP, if there is an error, there's no correction. But TCP, if there's an error, for example, data dropped or whatever, then should be re-requested or anyway it should be fixed. That is one thing. Another one is connection oriented and connectionless. So what does that mean to us or to the system or protocols? That's what I want you to understand now today. Okay. Um, so with this basic background, you may be able to learn, for example, next time, the course that I am usually teach is a wireless network. Um, of course, there is a connectionless. So only at the time that you talk or at the time you send SMS, then there is a connection. It's not really connection, but the packets are transferred. So all such things will be discussed in that class. But for today, so very, very, very basic uh, material that I want you to understand is this. There's a physical communication and logical communication, right? The all physical layer is only the bottom layer. If you can recall 7 layer of network architecture, physical is lower. Other than that, all the physical description and and controlled by software only, right? At the top of the application layer, which is the layer that you can play when you send some message or email, or when you link to the web server, whatever you do, it starts from application, and then each packet is a small chunk of the message that you send, even if the message you want to send is very big and very large. For example, your photo or video clips, very big. They are not all to be traveled together as a large volume. Usually it is chopped into the small size, which is packets, we call that. So each packet has some header attachment. Header can describe a little differently as the packet travels from top to all the way down, which is a physical line. So as it passes each layer attach the header. So header will be increasing by the time the packet reaches the physical layer increases. and altogether travels along the physical line. When it reaches the destination, a particular port, through that port, there's a physical line, and then it traverses backward from lower to upper all the way to the application. So you and your opponent are now using the same application. For example, as it traverses backward from lower to the top, at each layer, it can pick up the packet. We call that unpacking. So at the origin source site, at each level, the packet is traversed from top to bottom. Packets are packed with the header. At the destination site, it's a reverse, so from bottom to top. At each level, unpack, and then any specific layer, or they pull out the packet information and understand what it is, okay, and then push it to the one level up and another, all the way it reaches the application layer. At that time, your friend, your opponent, may be able to see the message that you send. Okay. Yes. Oh, this is not. Oh. Oh. Okay. So that's what it is. Says here. Transport protocol run in end systems. So this is sender. This is the receiver. Sender has also application layer, transport layer, network layer, data link layer, and physical layer, right? And same thing at the other side of your communication. Real linkage between this and your source and destination is physical line. That's what we are looking at right now. If you are taking, for example, wireless communication, but there is no physical line in between, right? Physical line, then it goes through that guided cables, for example. Yeah, fiber optics or whatever you can think of. But wireless, there's no such things. Okay, so you look at how the wireless can transfer. But anyway, this is the physical line, okay, from here to the destination. So at the sender side, uh, breaks application message into the segment. We call this segment packets. So as so at the transport layer, it uh, it split, decompose the bigger message into the smaller size, which is a packet, and when each packet moves down to network layer and data link layer, and at every time a corresponding header is attached to the packets. The packets originally containing only the message is called payload, right? So to the payload, the header is attached. So there's a different kinds of headers: IP header, TCP header, and so on and so forth, right? So all the different types of headers can be unpacked at the receiver side. That's why we are going to look at today, maybe today, or till next week. It cannot be done in any but Python. I mean the language, okay, the programming language. You could see that in Wireshark, but Wireshark already cooked everything. So you can click and see what's going on. So visualization. It's a complete application tools, but there's no room that you can manipulate the way that you want to control. Okay, so a little bit of introduction. Codings already provided to you. Okay, we may not cover everything there, but those who are interested in can make your own progress. But we'll start a little bit so that you can get a clear idea. So there's a sender side, and at the receiver side, there's another process, reassembling. So once we break down and then break into the packets, at the receiver side, reassemble. Thing is this: at the sender side, the message is broken into the small, and all headers are assembled into the packet. Okay, so break down and assemble. Breakdown of the message. Assemble the header at the sender side. So as it moves down, the header is more header is attached into the packets. So this is a payload, and more headers are attached. So in this way, I would say assemble, but in this way, I said that is a break. This is a break, and this is rather than assembling, I said attach. Okay, at the receiver side, it's backward. The packets are reassembled. As it arrives packet by packet at the application, you may be able to see the entire message. If it is the email, then through the TCP protocol, so you should see the complete message. Exact same message was originally shipped out. I'll get back to you. But the headers, let's say when it arrives, then we have a payload and multiple headers attached to the packets. As it moves up, packet is unpacked level by level. So we have a payload. When it arrives at the higher level, so one header is unpacked and recognized, and therefore packets can be properly processed. Okay, as it moves back up here. So I wanted to understand what you mean by breaking out and assembling. I want to know in what way we say attach and unpack. Okay, Eric, question?
I understand what you mean by the assembly and disassembly and how it goes in order. But each one of those headers, is it similar to like a header that is on a hard disk?
It describes everything about that message. For example, what is the origin source? What is the destination? What is the port numbers? So that it should be delivered properly to the right place.
So when you say like port number, it could be simple as similar to like this message is going to port 23. This is a telnet.
Correct. Message. Yeah. If it is a telnet message, then okay, at the destination, for example, www NewYorkTimes.com. That is a specific telnet port or FTP port. So it goes into that port.
And that information, that's
That's all such information described in that header, right? Otherwise, the packet itself cannot travel, right? And also, more importantly, each packet has a packet sequence. Therefore, when it is to be reassembled, according to that packet sequence, it can be lined up properly. You've never seen any email messages scrambled mixed, right? It's always in the right order, right? Sentence or paragraph by paragraph by paragraph. Right? This is a TCP. So we are looking at more rigorous way of sending and receiving messages. UDP is a little different. UDP, when you watch some video, audio, even if there is some missing, we still let it go, okay? It doesn't affect for you to understand or interpret entire, right? Even if some missing, still it is better to go, move on, than wait and make sure that all the packets are successfully received, right? There's a lot of waiting. Therefore, another protocol developed, so it moves on. More practically, when you call someone, it's a voice, which is one of multimedia type, right? When you call somebody and voice dropped, what if some protocol applied to you? You should be make sure that. So wait to receive that dropped voice message while you are still talking. There's a lot of congestion, and you may hear the opponent's message like a minute later, or 2 minutes later, right? A lot of latencies occur. That's what you do not want, right? Even if some drops, sometimes a lot of voice dropped. Very simple. You can say, "What did you say?" Then it can be re-spoken, right? So more human involved and human tolerant. Human tolerance is involved. So we do not really care, and we think better to move on. So that is a UDP. Okay, so this slide explains the difference between transport versus network layer. See here, transport layer and network layer, there's one level, upper and lower. So we better understand the network layer tells you logical communication between host. So between host. This is a between process, transport layer. What is a host? Like your laptop, right? That is called the host. Your device. So at the network layer, it describes about the protocol between the host, two laptops, for example. Transport layer describes the program, what program that you are working on right now. If you pull up, for example, database client, then database client is a process. What is a process? Process is nothing but a program. When a program is loaded in your system and up and running, from the operating system point of view, it is called process. The same objects, same object is called program if it is stored in your hard drive. We call that program, or even file. File, which is a program, right? At the physical layer, we call it file. At the logical layer, we call that program. It's a computer program, or whatever the coding, right? When it is in the process, in the CPU and running, then it is called the process. Source and destination. Two people are using the same, or maybe doesn't matter, same or different, a process. A program is up and running, so we call that process. So one process at the source wants to talk to another processor at the destination. So two process needs to be described. That can be done at which layer? Transport layer. So at the transport layer, here, this guy says, oh, we are running on some program 1 and program 2, whatever, right? And then the proper header describes about that. Okay, this guy, sender side, this guy is running right now Microsoft Word. Okay, at the network layer, by the way, that Microsoft Word should be sent to another system at the destination system, maybe MacBook. So MacBook has its own logical name, right? Whatever that name, or we call that IP address. Okay. So that is that. Internet Transport Layer protocols. There are two protocols developed and widely used. TCP is reliable. So any messages that you want to make sure successfully delivered, then TCP protocol is used. Very good. And that is in order delivery, because a packet has a sequence numbers. UDP, unreliable, if dropped. And unordered delivery. You may be able to see not recent technology, but many years ago, sometimes you have disordered the messages. When you watch online videos, then somehow scenes is moving forward, and all of a sudden, unrelated scene comes up and then move further, like 1/10 a second. So you may be able to see that. That's unordered UDP. And TCP, therefore, congestion needs to be controlled, and flow control, and connection needs to be set up. On the other hand, UDP, no frills extension of best effort IP, which means there is no connection. Connection, once it reaches, then that is, at that moment, there is a connection. And after that, no connection. So multiplexing and demultiplexing is, this multiplexing and demultiplexing is always the foundation technology in networking. Doesn't matter wireless or wired. While multiplexing and demultiplexing, you may be able to do encode and decode. Okay, as message is encoded or decoded, you may be able to do, for example, compression and decompression. Therefore, size of data can be properly manipulated. And also some security issues if you want to encrypt so that no one else can understand yours, especially when you connect to your banking system, then encryption is very, very important, right? So that is encrypted. So all detailed utility programs are executing when multiplexing and demultiplexing is performed at the same time. That is done in this transport layer. When data is sent from the source, then there is a multiplexing. As it arrives at the destination, then demultiplexing is used. For example, um, compression, okay? Multimedia, video clips compressed. Therefore, proper size of data can be handled more efficiently. The compression mechanism applied at this transport layer of sender side. As it arrives at the destination, which is where there is a transport layer also. So as it arrives here, then it should be decompressed. Therefore, the proper message can be shown at the destination. Socket here, we say here process. Process is nothing but program, right? Each program, as it is installed, then socket is assigned. Socket means a port number. Port number is assigned. TCP communication, then 23 port number is assigned. If you want to access a web page, web browser, then port number 80. Or if you want to access a secured port, secured web servers, then 443. And if you want to access, for example, the system shell, remote Linux operating systems, if you want to get into that Linux operating systems in secure communication, we call that secure shell, SSH, right? Then port number is 22. And each program has a different port number. When you install database systems on your machine, then database system asks you to assign a port number. And the destination database, it has also its own port number. If you want to enable your database to talk to the remote database, then you have to always specify properly the remote host name and port number. Therefore, for example, from your program P3, let's say this is a database, MySQL, then it has its own port number. So this program is listened to that port number only. Okay? Not all programs listen to all the ports. Only one port assigned. So listen to it. if that port says, oh, there is a message arrives, then it can take that message in. Or your MySQL wants to send the data to the remote database, then your MySQL use this designated port. As it arrives at the destination, as I said, the remote host and port number needs to be specified. So when this guy, second communication, arrives here, then at the transport layer, this guy understands which port it should go in. Therefore, this program and that program can eventually talk, right? Physically through this communication protocol. So there's a multiplexing and demultiplexing. That's what I talked to you. And then this is a header. The structure, data structure of headers. To some of you, particularly Eric. TCP, UDP has this kind of header information. Because at the transport layer, concerning the port number, so source port and destination port needs to be described. And then other header fields. So we, my handouts, the textbook has, if you see, okay. Anyway, if you turn, I think the last from back. Oh yeah, second last or third last, yeah. Third last page. There's a table. Did you see that? There's a table. And I described IP header and TCP header. If you see here IP header, the size of IP header is what? I want you to figure that out. What is the size of IP header?
Size in how many bits?
How many bits or how many bytes? So one row is 4 byte long, right? 32. It starts from 0. So 32 bits, which is 4 bytes. So one row, 4 bytes. How many rows? 1, 2, 3, 4, 5, 6. So 6 times 4 means 64. So 64 bytes long header is formed at the network layer and attached to the payload. TCP, this header, how many rows? See here, at the end of 31, the bit number. And the next line is identification code described in 2 bytes starting from 32nd bit or 33rd bit, right? And after that, flags. There are 3-bit flags. And after that, the rest, 1 byte and 5 more bits, which is 13 bits. indicates fragment offset, and after that, time to live in 1 byte, protocol in 1 byte, and header checksum in 2 bytes. And after that, 4 byte long source address and 4 byte long destination address. Why 4 bytes long? IP address usually 4 byte long, right? If there is a 4 byte long IP address. There is a IPv6 different version, but we are now talking about older fashions. So IP number has 4 numbers combined, right? Each there is a dot. So we can say 129 dot, 168 dot, 1.1, then that is usually your laptop or home address, right? Home IP, your source IP. Destination IP needs to be described in 4 bytes also. And there are some options in 3 bytes. And then finally, padding. What is padding? One byte long padding. By having that 1 byte long, so all in one sequence of bits, right? Ones and zeros. So by knowing that padding, 1 byte long, that we clearly understand, oh, this is the end of that IP header, and followed by TCP header. So there is some delimiter between header files. If you see this table, then we can clearly see, oh, there's 2 different headers. But actually, headers attached to the payload. Then all the message is one sequence. Therefore, there should be some spaces in between. That's a padding, so 1 byte. Question from Edmund?
Let's say it's 0.7. So why do we say 1 byte is like
0.7?
Yeah.
Where are you?
From the padding, for example. It's not like 1 byte, right?
1, 2, 3, 4, 5, 6, 7, 8. It is 1 byte. Count the bits. 7.5? There's no half bit. So 8 bits, which is 1 byte.
Each one of the dashes is a byte, or is a bit.
Clear? So that is exactly similar to this. So TCP and UDP formats, ours is a little more detailed, right? On our handout. TCP header, first two bytes for source port, and then followed by 2 bytes of destination ports. So 16 bits to be used to indicate port number. Then you can calculate how many ports theoretically possible at each host. How many ports possible? 2 to the power 16. 16, and actually -1. Why -1? There's no port number all zeros. Maybe so, right? Well, port number 0 may be allocated. But anyway, 2 to the power 16. Now, how many? I think 65 some thousand, right? That's a 2 to the power 16. We can calculate that from our
65,535.
Yeah, that many ports are available. Are we using all of those ports? Usually not. Do we use any ports of that? For example, if we have a USB plugged in, that's one port. If you have in your desktop, for example, keyboard, then keyboard, there's one port used. Mouse, there's a separate port. Terminal, that is another port. Therefore, if you type here, if you want to see the character that you as you type, then the keyboard and printer communicate through those designated ports. Laptop has also ports, but it is not shown to you internally. It is linked through that ports, laptop-wise, because there is one single components, right? Okay, so this other header fields can be described in my handouts, where there is a sequence number. Why sequence number is described here? Because the message breaking out is performed at the transport layer, right? At the transport layer, therefore, we can form for TCP protocol or UDP protocol. So that's a sequence number of the packets described here. Acknowledgement. So whether it is fully arrives or data offset reserved, and there are 1, 2, 3, 4, 5, 6 bits. Each bit allocated some something, right? The second one is acknowledgement and PSH, PST, SYN for synchronize, and fin maybe finalize, and followed by 2 bytes about the windows, and then another 2 bytes for checksum. Checksum usually is checked by 16-bit long, and urgent point options, and again we have a padding, 1 byte long padding, followed by real data. This is real data. We call that payload. So right before this real data, we have a 1 byte long padding. This is a simple space, indicates delimiters between 2 different descriptions. Okay. And connection lists at the multiplexing, we may be able to see here. This is better. Connection list. If it is a connection list, then port is assigned, say 9157. This is an example. And then 5775, another port. And then 6428. So each host set up a port number. The port number is used for the connection list communication, which is a UDP. So through this communication, any messages go through that common port. When at every time when a message needs to be sent out or to be received, that port number is used. Designated port number, not designated, yeah, allocated port number is used. Doesn't matter the program, doesn't matter the process. As far as it is UDP, then it goes through that allocated port number, which is not the same as connection oriented. The connection oriented, each program, see P3, you can say process P3 talk to process P4 only through this port number. Although look at this host. There's application, multiple applications running, but each application has its own designated port number. Therefore, for example, at the third host, if it wants to communicate with the process P6 in the middle host, then the port number this and port number that, those two ports needs to be agreed, and therefore they can communicate. So at each time in your packet, that port number needs to be specified. This port number needs to be specified. In the middle host, if this P4 wants to talk to the P3 over here, then it should say, okay, port number 80. Actually, port number 80. This packet goes that way. Okay, it doesn't really matter. And then here, this is a host address IP A, address IP B, and IP 3. And so at each time here, I think this goes to that header, and this information is the header to this packets. Packets from A2. Oh, it is right. It is right. Yeah. So here clearly says source IP and port number. Source IP is B and port number 80. So actually this is port number 80 from the source IP B. Okay, so from this host and port number, this packet is traveled to the destination, which is A. Port IP address A, port number 9157. So this port number is 9157. Okay, and look at this packet. If you see this packet, then that is a source IP and port number, which is describes here, right? So TCP is source port and destination. So source is C, as you can see, C. The port number is 5775. So this port number is 5775. This is source, and destination is B, which is in the middle, and port number is 80. So this is again 80. This is not a good idea. Should be written here. Anyway, this is one port. It's not two ports with the same ID. So one port, one ID. So if I revise this, then it should be, this goes to that IP. Because this is 80. This may be something else. 88, let's say. And P3 comes from the middle host. So in the middle host, go to middle host. Coming from the port IPC and port number 9157. So 9157 is here. 9157. Oh, I'm sorry. 9157 is here. 9157. That is the source IP. And then destination IP is again 80. So this goes to 80 again here. All right. So all 80s. But process P4 is listening to port number 80, and P5 listening to port number 80, and another program P6 is listening to the port number 80. Multiple program can listen to the same port. That is possible, right? This is a connection oriented communication. This is TCP, and previous, there is UDP. UDP is called User Datagram Protocol. Segment may be lost, delivered out of order. There's a connectionless, which means no handshaking is needed. The two ports doesn't need to be agreed each other. Handshaking is nothing but some agreement of further communication. Yeah. When you want to talk to someone, then first thing that you need to do is, hey, I am who, and then shake hands. Then he replies who that person is, and then you can say, can I talk to you? And then that person replied to you, yeah, why not? So four-way communication usually needed for handshaking. You need to first to say who you are, and then opponent to say who that person is, and then you can say request. Mhm. That's fine too. Yeah. Question. UDP is what? User defined. What do you mean by user defined? Oh, that's different. Static or dynamic IP is a different issue. Thing is this. Okay, so I need to explain that. IP, the typical IP uses 4 bytes. So each byte can identify 256 numbers from 0 to 255, right? So we have 4 of such possibilities. So 256 times, 256 times, 256 times, and 256. That is full possible numbers that can be identified by 4-byte long IP address. If we assign one IP to one host, then definitely impossible to assign all the IPs available in the world. About 20 or 30 years ago, it was possible. So each system, when I studied, each system has its own IP, which means we can attack very, very easily at that time. And each system, there's no much security equipment installed. So what happens is that if I have and also we can break in the super user very easily in the system. So when I was since I break in the super user, and then I access to the andrew.cmu.edu. Andrew at that time is very leading still. So, Carnegie Mellon's Andrew system, right? Is it Andrew Carnegie or is the name of the person? Or Andrew Mellon? Whatever, right? So Andrew systems. So I get in and I can see whatever I want to do, right? This is a 20 years old, right? Very easily. But these days, almost impossible, right? They set up firewalls and DMZs and all different security equipments and security software installed and running. So it bounces you. But anyway, so each system has IP. But right now, impossible to assign one IP to each host. So what do we need to do is that at least there should be at least one IP address needs to be assigned to the subdomain. Okay, like mercy.edu, then I do not know how many static IPs that we are subscribing, but we have limited, right? Vigo University has, for example, 255 static IPs, or Stanford has 255 times 255 IP address. Mercy, I don't know, maybe 1632 IP address. Um, Give me a break. Let me finish a little bit. Um, so, Mercy has a few static IP addresses, but we know that Mercy College has thousands hosts set up and running. How come each host receives data then? There's no IP, right? Therefore, each domain, like mercy.edu, has its own um, um, translation utility running. Translation means IP address to the world. That's a static IP address. So this guy can talk to the outside. Internally, this guy handles its own IP address. This internal IP address is not known from outside. From outside, they can understand Mercy College as a whole with the specific IP address. But each system of yours needs to receive and send, right? Then there is another component, IP, let's say translator, address translator. That translator, when it receives, this translator understands, identify all the host, each host. This guy says, oh, this message goes to that host. Another message goes to another host. So this guy is handling for internal messages. So this guy receives all the messages that comes to Mercy College, and then from there, this guy is distributing the messages. We call that dynamic IP. Usually, internally, this guy wants to set up dynamic IPs. Usually, dynamic IPs. Why? We still do not know the expansion of the host family. Okay, how many hosts that we would have? So we do not assign the physical IP address to your laptop, rather dynamically. As you connect, then assign IP. If you disconnect, then that IP can be assigned to someone else. So we have limited IPs. So upon request, one IP is assigned to that guy. Time sharing. Okay, that is what dynamic IP address, and that is what static IP address. So from outside comes to all of us. The message to all of us, each different messages, comes through the same network equipment, which is installed for Mercy College. When it arrives there, then that equipment also distributes. This message goes to person 1, this message goes to person 2, and person 3, and so all the way to me, right? At worst case, if all the dynamic IP address is used currently, and there is one more guy try to connect and wait for dynamic IP, then there is no way until there's one guy disconnects. There's a limited set. Therefore, sometimes if you want to access, you do not have no connection. You have to wait, right? If you go to Starbucks, if there are tons of guys working their laptops, then you may not get IP address, right? That is the case. Okay. UDP has a smaller. This is similar to length and checksum. So we have TCP header this and UDP header. Do I have UDP header? Oh, so I didn't have it. I didn't add the UDP header, but I want to put the UDP header in the next version of this. So it has a source port number and destination port number. Up to this is the same as TCP, right? And then we have length and checksum and payload. There's a UDP checksum, and TCP has a little complicated sequence number, which is not available in UDP, right? So order is not important in UDP protocol, but TCP we need to have a sequence number and acknowledgement number. And see here there are multiple indicator in single bits. U means urgent data, generally not used. ACK, acknowledgement number and acknowledgement valid. And P for push data now, generally not used. All for ready to what? RST. Some of this. This is for synchronized. This is for something. All this description can be found more clearly. I described somewhere in the second page from the last, and I said more detailed description. For that is, if you go to www.networksorcery.com, okay, second last page of the handout, right above example 3.54, there is the URL www.networksorcery.com. If you go there, and describes everything about network indication. I want you to click RFC source book, then you can see IP protocol suites and TCP IP ports. So if you click TCP UDP ports, connection is no good. Wait. TCP UDP ports. Or you can click on IP protocol suites. This is better. Okay, and there is a for example IP. Are you following this IP? Internal protocol, and describes everything about that. For example, first bits indicates the version, then there is a version information. If the first bit is said 0001, I mean 0010, oh no, 0100, If it has 0100, then that is IP protocol. That is a version number. And then second 4 bits is IHL. What that IHL means can be found by clicking this IHL. That is called the internet header length. So header, so 4 bits indicates, it's not the length of 4 bits, but it indicates, for example, if it says, oh, where is it? Here. Specify the length of IP packet header in 32-bit words. 32-bit words. 2 to the power 4.
Protocols access.
32-bit words. The maximum number is valid 5. And then differentiated service, 8 bits. It can indicate, for example, first 6 bits for code point, and the next 2 bits unused, which means if it is 0000, then that it means something, right? So you may be able to look it up. So it describes there. Let's see TCP, if we have any TCP. It's not, okay. It's not available, TCP UDP ports. So header of TCP. Oh, here, TCP. Click that TCP. Again, TCP is. But anyway, you can see it, all descriptions, which means oh, yeah, you can, but not to me. That's okay. Good to you, Anthony. Okay, here. So it describes what it means, okay? So according to this description, then you can do programming. Okay? This is the end of theory of the network, the important theory only. So we know TCP/IP and overall techniques. Then we'll take about 15-minute break, and then hands-on lab. So we'll do socket programming. There are a lot of tutorials available. So on your own, I want you to take a look some of those. If you want to learn IP or TCP, UDP protocol, detailed description, it's a complete and fine granular level of descriptions available in this web page, www.networksorcery.com, we just looked at minutes ago. And those who wants to read this struct module is a module that you need to import. This is a very, very important module when you do struct. Therefore, structuring of the packets. If you want to packing it or unpack it, the structure module needs to be used. So what I want to do is to look at that struct explanations. So what I'm going to do is I'm going to copy this to the web browser, and we all need to look for it. Okay, there's a struct, which means this is a module that helps you to interpret bytes as packed binary data. Packed binary data. So packets, the data is already packed with the headers and payload. when you receive a packet, then it has a IP header, and it describes whether it has TCP or UDP. Therefore, UDP header or TCP header. Not all the packets one of the other these two, but more than that, right? For example, first time if your device wants to set up handshaking, then each message between two parties, two devices, is again that is a separate packet. If you say, hello, I am John Yoon, then that is one packet. And then your opponent says, hey, I'm Smith, then there's another packet. And if I reply to that person, I want to talk to you, then that is another packet. And if it says acknowledgement, okay, ready to talk, then there is another packet. So after the successful handshaking, then you need to now send data, right? If it is a small data set, then there is one packet. At that time, because that is a data transmission, so either TCP or TCP or UDP is used, and therefore packing is properly done and also automatically done as you send packets. Somewhere in the middle or at the destination, when the packet arrives, then it is unpacked automatically also. What we are going to do here, we want to not the intercepting, but we still want to see the packets and manually unpack it. In order to unpack, then we need to use this struct modules. So there is a functions available: pack, pack into, unpack, and unpack from, iteration of unpack, and cat size. So those are the functions that you can use and also format characters. If yours is signed characters, then it specifies B. If you want to have unsigned short, which is an integer, which binary code is integer, right? So there's a binary code. But if you want to read it, if you know for sure the packed data is integer or float or bytes, and therefore the size of, for example, if you say capital H, then there is a 2 integer size, and followed by 4 integer size long, which is L, small l, or uppercase L, there's another 4 byte long, and 8 byte long of integer, then we need to say Q or capital Q, and so on and so forth. What I mean by that here is, if you we'll get back to this again, but because we have a struct, I want to look at the example 3.54, which is the second page from the last of the handout. then there is a Python programs. The first two lines is to import the modules, socket and struct. Two modules needs to be imported. And then I want you to look at line number 19. Line number 19. There is a struct dot unpack. Unpack function is called, right? If you look at unpack, then it's within the first argument is within string exclamation mark uppercase B, uppercase B, uppercase H, 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 B, B, H, 4 small s, 4 small s. What does that mean is that I want to read the second argument, data from the index 21. I want to read from that point, I want to read in that way. Exclamation B, B, H, H, B, B, H. What does that mean here is in this struct modules 7.1.2.1 byte order size and alignment, there's a character question mark means I want to read from the network. That's what I mean by here. You know that in string it starts from question mark, right? It doesn't mean that I want to read it from any standard little Indian or big Indian, but I want to read it network packets in big Indian. Big Indian and little Indian, there is another term that you may be able to understand from computer organization or some other course, right? If it is a big Indian, then the most significant bits appears top. Okay, little Indian is less significant bits the top. Therefore, for example, money-wise, if I describe 1, 2, 3, 4, if I say 1, 2, 3, 4, then what is the number for money? $1,234, right? So which one is the most significant number? 1 or 4? 1, right? 1 is the most significant number. You don't care the last, the number 4 or 5. You don't care, right? Even if that goes to 0, then still okay, as far as you have 1,000, a little bit over 1,000, right? There's a so-called big Indian. Little Indian is, I want to make it a reverse. The first comes, smaller number is important. You may describe the same value in different order, right? For $1,234 can be described in this way, 4, 3, 2, 1. And then you can say that it's a little Indian. Then it means from backward, $1,234. So what is the most significant bits? The single bits rather than fourth bits, right? That type of things. But anyway, if it is network, then it starts from the question mark. And then coming down here, you want to read the first 1 bytes, which is unsigned character, and next one is also 1 byte. Because we said uppercase B and uppercase B. This is very, very scientific. What that means is that when you come back here, IP protocol and IP here, then you can see, I want to read, if you see this structure, I want to read 1 byte. I want to read another byte. BB stands for I want to read byte by byte, followed by uppercase H, which means I want to read 2 bytes, uppercase H, another 2 bytes, and then another 2 bytes, H, 3 H's, and then B again. So 1 byte for TTL, 1 byte for protocol, and another 2 bytes, header checksum, that's for H, and then 4S, and 4S, which means 4 byte long of source IP address and 4 byte long destination IP address. This is very, very important factor when you do structured programming. Okay, so whatever those data structures that you can see from IP header is explicitly specified here in the line number 19 of example 3.5.4. Because I said there, unpack function takes first argument in string, and then there's a code, exclamation, BB, HHH, BB, H, 4S, 4S. This covers all of this. Okay? This is for IP only. If you want to see TCP, then you need to describe that way for TCP. You want to do that? TCP is first 2 bytes for source. So that what do you need to do? Uppercase H, right? Uppercase H, and sequence number 4S, acknowledgement number 4S, and then we can have a B, H, I think 3S and 1B. If we read that much, then it describes about TCP header followed by payload. At that point, you can see the payload. If you want to hack in and see the message content, then you need to go up to that point that you can capture the significant data messages. You can grab that data and apply for decryption mechanism. Okay, using cryptography technologies, you can encrypt it, therefore find out bank user ID and password, for example, right? If you are so bad guy, then you can do that, which I do not encourage you, but I encourage you to understand the technologies. Okay, that's what I want to say. Okay, so that is for this format string, which is very, very essential for your Python programming to unpack IP packets and TCP packets all the way up to the payload, so that you can break in the user messages. Clear? Understand? So ready to hack in the network? No, I'm asking you. Are you ready to? Although I do not recommend you, because that is somehow involves criminal, cyber criminology. Yeah. No, I clearly said, don't do it. Okay.
but understand how it works. Therefore, you can be hired by NSA or FBI, DHS, NGA, CIA, all those special agencies. Okay, I want to when you, I want all of you to be hired by important agencies, national agencies. Um, as I made an announcement a few weeks ago. We're going to we already started officially the, the second cyber skill competition at Mercy. So any of you, I think all of you can participate if you bring a team. If you want to do that alone, possible, but less likely to be the winner. If you include more of your best friends in programming and hacking, then you can participate. It doesn't matter if you bring 100 people as one team, fine. But if you have so many, then you don't make efficient progress. Whoever you want to bring, not necessarily here at Mercy students only. You can bring some students from MIT, Stanford, Caltech, Carnegie Mellon, yeah. Um, and at this time, we will have sponsorships. Uh, the company, NetVest, so they're going to do. Uh, I've discussed with those guys. So I requested my desire, but they will decide. Okay, I request a little bigger money, but we'll see. The competition will end by the end of spring semester. So I would say in May, mid-May. What we will do is, if once you form a team, then we set up a regular meeting uh, every Saturday. That's what we've done for the first competition. I join every other week, and students come here, and then they do work. Um, and each team can share the information. So it has a lot of synergy effect. Okay. Another side effect is that if you, yeah, for the winner teams, on behalf of them, our faculty members can tell outside. Okay, propaganda. It's not really propaganda, but we can sell your team, your products. So more effectively, you can be exposed to the world. For example, we can recommend it to NSA so they can hire quicker than usual. Remember that four students already hired by NSA, they already started working there. Those are all students got some work done, demonstrable. So when they visit us, we want to ask them to give us a demo, give demo to NSA key players. So when they see the students' work here, we do not show any work to NSA. We want to show some selected work to NSA so they can see them and they can hire quicker. So all of those guys made a demonstration to NSA. So they are already there. We still have about 10 students. They already submitted their resumes, but sometimes no response. Sometimes they made progress, but slowly. Slowly means if they find someone else from somewhere they want to replace them. So the best and most effective way that you can be exposed is through that competition. Then we can sell you and your products. Think of that. It's very, very efficient. Okay, so by the end of your graduation, you'll be hired. Got it? So form a competition team. You can bring anyone. Yeah, as far as there is at least one student in a team can be eligible. Okay.
Let's move on. Coding. Visit by Python socket. Remember the socket is a module that we need to import. So we need to see the socket also. Copy the code from the network sniffer and then roll sockets on the Windows and Stanford. So we'll do this step by step. If you open up the handout, my textbook, we are now chapter 3 and section 3.5, which is accessing networks. And I described some basic there. 3.5.1, client and server programming. That's what we are going to do today, okay? Not yet network unpacking program. Client and server programs. I gave you an example. We are now on the third page from the beginning. There is an example 3.5.1. I want you to write Python script, my server and my client. Those two programs already there. Okay, so I want you to write my server and my client. Two files, two separate files. One file is called myserver.py, another myclient.py, which is in the third page. And what you need to do is the figure above that coding list, there's a server start and client can talk. So what you need to do is that you need to start a server. How? The way that you initiate, right? C:\python 34\python followed by myserver.py, then your server will be ready. Okay, there is one command line window. So you need to open another command line window. Don't use the same command line windows. You cannot. You need to bring up two windows, two command line windows. Another command line windows, there you run myclient.py, and then you start typing. That's what I want you to do. Okay. Once you taste that, then this slide makes more sense to you. Let's try. I think by this time you want to see why you need to say, for example, some of this bind or listen, right? So this is some of the sequence that you need to set up the server, and the right column is the functions, sequence of functions that you need to do. This is a general idea. Therefore, you need to find out the similar functions, availability of similar functions in your language. For example, Python. Okay. To do that, you need to open up and there you can say Python socket. And then there is a Python sockets. Let me open this. Okay, this is version 3.5. Whatever version that you want to do, but I think basic functions remains the same. But although, because I'm running Python 3.4, change it to 3.4, it doesn't change, which is good. So you need to read. So what I want to point out here is this is a socket. Socket object needs to be created first. Socket object can be created by the constructor called the socket open and close parenthesis, right? And it takes 2 or 3 parameters as the socket object is constructed. The parameters, the first parameter is one of this socket family. Second parameter is socket type, and then finally protocol. It is described somewhere here, I guess. Or I put there on my textbook somewhere. Let me bring up my textbook also. Okay, this is the textbook that you may be able to see. See, there is a, if you see this, we do not cover here in this class, but Python programs access the financial data and automatically put that on, and open up Excel workspace and plug the data there, and then Excel data can be also saved in a file, and then we eventually call some statistical utilities to run the data that we saves. Those are in another modules, but we are not going to do that here. Okay, this is accessing networks. Here, the socket related function to be used include the socket function. This is not actually function. This is in your object-oriented concept. This is a constructor, object constructor, if you understand what it means, okay? So by running this function like the method, an object of the socket is created, which is available in socket module, all small case. Socket constructor takes 2 or more parameters. The first parameter is to describe family. Second parameter is the type. And third parameter is the protocol, and so on and so forth. Family of the network can be one of, did I say somewhere? Yeah, I said here, the constant to be used includes, yeah, AF Unix, AF init, AF init 6, this is a type, family. Here, AF init, and then I probably said that somewhere. Or did I do that? Okay. Yeah, I'll add. But anyway, that is the family needs to be specified. In our case, AF init, right? AF underscore init. This is another typo. AF underscore init. And then type is sock stream. So you can receive the streaming data from, between server and client. And then protocol can be specified, but in your exercise, we didn't say that. Okay. So back to our slide. You first need to create an object of socket by calling socket function. And then that object, socket object, needs to bind to the host and the port number. If you want to bind the host, which is the same as your program is running, then you can simply quote, open quote and close quote. Some of the common error is that if you open quote, space, quote, then your Python try to interpret the space in between. So there's a bind. After that, listen. Okay, listen number one, then how many listen do you want to do? So listen 100, listen something, okay? So you want to, yeah, usually at one particular time. So, concurrent time. It's a very, it's like millisecond, okay? So even if one and if you access manually, then it works, still works, because a little bit of a difference, right? Unless you do by programming request at the same time, as I said, probably earlier. In order to do that, you have to run the program, not by manual. So manual, there's always enough space, enough time elapsed. So it's not, computer clock time is not the time that we can imagine. Right now, what is some 1 billionth second, right? Which is giga. Our clock speed is 2 point some, right? What is hertz of your 1.9 gigahertz, something like that, right? Current laptop technologies, which is your system clock time. If you want to differentiate, then you have to click the client's request 1 billionth time, within 1 billionth time difference. We cannot do that, right? Almost impossible. But anyway, it's a listen. So if you see that your program is here. See here? So we create an object of socket, which is called S, and that object binds to the host. Again here, double parentheses, which means you can specify here, for example, server equals, you can specify 10530, and then come here, you can do host, server, or serve. It should work in this way. Now you know why it has double parentheses, right? You want to combine host and port number. as one, and then that together can be used as a parameter to bind the function. And after that, your server socket is ready to listen. Okay. And then there is a loop. Once client request, then you may be able to accept it. Client request can be accepted, which is here. You accept your server socket accept. So always accept in this case. Again, if you want to accept selectively, what do you need to do? You need to first, anyway, internally accept it, and then find out if it is linked from a reliable client. How do you know reliable client? By looking at remote IP and remote port number. See here, there is a connection information and a remote IP and remote port number that is returned from this function. So by looking at this remote host information, you can selectively remain the connection. Okay. Do you see the extension of this? Yeah. Or you can do, if that is, if you want to control the list of user members, usually in banking system, they want to verify your host, right? Not only your login ID and password, usually they check the host. If there is a new host, then they need to still verify whether that is a reliable host. Once you do that, then from that time, your host is remembered by your banking systems. How it is controlled? It is controlled in this way. Your remote IP and port number, if it is not known, or if it is in the list that you want to serve, then it requests back to you, say, hey, are you using reliable or trusted the host? There may be someone on behalf of you sniffing. So to avoid that security holes, they want to handle this. Right? What they do is after they receive, there's one module here, one module, so that you have a list of trusted host ID, IP, and port number. If it is in that list, then you can continue to serve. Particularly trusted communications needs to set up that way. And then this is simply communication. After that, you communicate with the clients. The first thing that we did here is print. So remote IP is printed and remote port number is printed. So remote port number that you print here is not the port number you set up, 10530, right? Bill, what is the port number that you can see from the server? Port number of the clients. It's not 10530, right?
No, it's
Some other IP, right? It's the client.
Oh, yeah, I think it's 670.
I mean, yeah, that's not what I question. Question is not the port number for the server. Can you see the port number from the clients? That is written here.
at your server windows, then it displays the port number of the client. Eric, do you have?
127. That's the IP. 58.
And what is your server port?
I have 5251.
52521 is the server port or client port?
Yeah, so sure. Connect them back.
In your program, in your coding, what is the port number that you initially assigned? Same as mine? 10530? 10530 is the port for the server.
Oh, the server.
Right, there is a port server. I mean, yeah, server ports. And then at the server windows, there is another port printed, right? Once they are connected. That is a client port.
Oh, this is the client.
Yeah, client.
So this will be the
So from your same host, you have two ports open. One port for the server and another port from the client. They are talking. If you see the program here, the print RMIP and RMPT is from the accept from the client. That is displayed here. And after that, data sent from the client. That is written here. Data typically that is byte code. So you have to decode it. In that TCP/IP multiplexing, it is encoded. So simple decode is by calling decode. That way you can read it. All right. Meanwhile, okay, let's see here. So we have accept and read, write, in our case print, right? In our Python, rather than write, we have a print, and then close. This is a loop. That's what our server is doing. And on the other hand, at the client side, client should also open the sockets and then bind, connect, and print, read, and close. That you can see here. Although we start from main, but if you see the main function, then it has a socket object is constructed and then connect. From the server client side, you have to specify the host IP, not blank, like server here. And then you ask the user to type, and that data is sent by encoding, right? Data taken from user is encoded. So this is called multiplexing, and this is called demultiplexing. That's what we did. In the multiplexing, we did encoding. We would do compress. We would do encrypt if you want to do. Whatever we want to do. If you want to do a steganograph, so hide some message into the message that we want to send. Steganographies can be sneaked in. So a lot of threats can be made from the client side. So server side needs to be verified. The integrity of the data, right? So a lot of rooms in between client and server from this program. Any comments, any issue? Okay, so I explained that somewhere here, right? I explained that RMIP and RMPT, which is a remote port and a remote IP, and well, there is a server and client program. The exercise from there is currently our program shares one message and stop, and this exercise is to continue until you say so. Okay, and the next section is to network sniffing and network packet capturing. What you could do is, if you want to capture the networks, then you need to create an object in this way. AF underscore init, but AF underscore init is good for Windows. If you want to do for these similar ones in Linux operating systems, then you may need to use some other family. And also the socket here, this is a protocol. Protocol is IP protocol. IP protocol is handled where? Network layer, right? It's IP. And then you want to read not the data, but socket raw. You want to read raw data, it's binary data. Therefore, you can unpack it in our sniffing systems, right? That's what we want to do. So what you need to do in order to sniffer, this is the step. Acquire network interface. You need to plug your system into the network interface. You need to understand the network interface. Interface card, so-called the network card. If you want to do this wireless network, then WLAN 0, that is the usual interface logical name. Or Ether, if you want to do Ethernet communication. ETH0 or 1, 2, if you have Ethernet communication. So interface card needs to be specified, right? And then next step is to create an object of a raw socket. That's what we had here. This is a network object creation. And after that, bind the socket object to network and include IP headers, receive all packets, receive a packet header, receive packet data, and interpret the packet data. The way that you interpret can be successfully done using struct module. Struct module has unpack function. So use the unpack function. So here is a little bit of program. I want you to test this program, the example 3.52. See what happens, okay? 3.52. Program name is mysniffer1ip.py. So I want you to practice that and then we'll continue.